Alright guys, this is our second YouTube video regarding going virtual. Super excited. We're going to try something a little different today. I know my first video, the visual was a little off, with the camera being a little too far and things of that sort. So hopefully this video finds you a little nicer, okay? And hopefully you can see the information. Again, I'm not going to be posting the slides, so if you want, you're going to have to keep pause, play for this lecture, okay? So let's talk about it. So far we've talked about ionic bonds and covalent bonds. Ionic bonds are the stealing of electrons and covalent bonds are the sharing of electrons. But both of these bonds result from the attractions of positive and negative charges, electrostatic forces. Alright, but one of the things that sometimes we forget, covalent bonds and ionic bonds are attractions between two atoms. Alright, if we have two atoms that participate in a covalent bond, they make up a molecule. If we have two atoms that are interacting through a ionic bond, they form ionic compounds. Alright, in both of those cases, we're talking about two atoms that are bound to one another. Today, we're going to talk about how two molecules bind to one another. Alright, make sure you understand the difference. Covalent bonds bring two atoms together. We're going to talk about interactions that bring two molecules together, two compounds together. Alright, these are called intermolecular attractions. Intermolecular attractions. Covalent bonds are intramolecular. Intra refers to two atoms that make up a molecule. Inter refers to two molecules attracting to one another. Okay? Again, attractions between two or more molecules. You have to get that. Alright? Alright, so intermolecular attractions are weaker. They are weaker than ionic and they're weaker than covalent. Alright? So if we compare them to intramolecular reactions, those covalent and ionic bonds are much stronger. Alright, but they are extremely essential. They determine whether a molecular compound is a gas, a liquid, or a solid at room temperature. For an example, if we think about O2, which is a diatomic molecule, oxygen, our surrounding atmospheric oxygen, that compound is a gas at room temperature. The reason why it's a gas at room temperature is because those intermolecular attractions, the attractions between other O2 molecules, is very weak. So they have that liberty to be a gas. All right. Now there are three types of intermolecular attractions, and in summation we call them van der Waals forces. You can think of van der Waals forces as intermolecular attractions. They're the same thing. All right, we're just changing the name of them. All right, so intermolecular attractions, also we can call them van der Waals forces. There are three types of van der Waals forces, three types of intermolecular attractions. We have dipole-dipole forces, London dispersion forces, and hydrogen bonds. All right, so we have three types of them. And as always, when we talk about interactions between compounds, in this case compounds, or when we talk about the attractions between atoms, they result from electrostatic interactions. We're still talking about that underlying force that brings together positive and negative charges together. Alright, so intermolecular attractions result from electrostatic interactions. Alright, if you forgot what that term means, I encourage you to look it up. Alright, so let's talk about the first one, dipole-dipole forces. Now, in order for there to be a dipole-dipole force, first and foremost, you need to have a polar molecule. If you do not have a polar molecule, this force does not exist. The most significant number one thing that is required when having a dipole-dipole force interaction, you have to have a polar compound. If you have a non-polar compound, this dipole-dipole interaction does not exist. Only if there's a polar compound. Alright, so there's gonna be times where I give you guys examples where I'm gonna give you polar compounds, non-polar compounds, ionic compounds. It's up to you to remember that, okay, sweet, I have a polar compound, therefore it's gonna experience dipole-dipole forces. Alright? They occur when neutral but polar molecules are attracted to each other. You may think, well, why does it have to be a polar compound? All right, well, remember in the past that when we talked about polar compounds have a positive pole and they have a negative pole. The side that is negatively charged is because it has a stronger electronegativity value. Therefore, those shared electrons are going to spend majority of the time around that atom with a higher En value. Whereas this guy, since it has a lower En value, those electrons spend less of their time around that atom. Therefore, it gives it a partial positive. All right. So in this case, we can think of hydrochloric acid. Hydrochloric acid has one hydrogen and one chlorine. Hydrogen has a very, very low En value, a very low electronegativity value. Chlorine has an extremely high En value. Therefore, those shared electrons are going to spend majority of their time around the chlorine atom, affiliating it with a partial negative charge. Hydrogen is associated with a partial positive charge. All right, even though they're partial charges, they still have the characteristics of that charge. This partial negative is going to attract partial positives. This partial positive is going to attract partial negatives. So if you look here, let's assume that these are all hydrochloric acid compounds. All right, this is the hydrogen, this is the chlorine, hydrogen, chlorine, hydrogen, chlorine. In this case, notice that the partial negatively charged chlorine is attracting partial positively charged hydrogens from other compounds. This partial positive hydrogen is attracting other partial negative chlorines. So the reason why the dipole-dipole force requires there to be a polar compound is this idea here. We need to have a partial positive that attracts partial negatives. We have to have a partial negative that attracts partial positives. The definition of that dipole-dipole force is when we see that two compounds that have dipoles are attracting one another. Hydrochloric acid has it has a dipole, one positive pole, one negative pole, and it's attracting another hydrochloric acid, partial positive, partial negative. All right, so dipole-dipole forces are defined as two compounds that have dipoles that attract one another. They attract each other through their partial positive and partial negative charges. In this case, notice that we're still talking about the dipole-dipole, but we're talking about the repulsive forces. The partial positively charged hydrogen is going to repulse another partial positively charged hydrogen from another compound. The negatively charged chlorine is going to repulse other negatively charged chlorines from different compounds. Remember, intermolecular forces refer to attractions and repulsions from two different compounds. We're not talking about atoms. All right? Let's talk about another one. So that's just an example. We're not going to get to that. All right. I'm going to let my wife. All right. So, okay, sweet. So hopefully, that was your cue to press pause and write down the slide. Okay. The second intermolecular force I want to talk about are called London dispersion forces. You can also call them dispersion forces. Either one's fine with me. London dispersion forces or dispersion forces, whichever one you want to call. All right, now so the first one, dipole-dipole forces, there has to be a polar compound. In this one, every single compound exhibits this type of force. All right, whether you're polar, whether you're non-polar, whether you're ionic, everything experiences these type of forces. All right, so that's the very most crucial factor that you have to remember. Everything experiences London dispersion forces. So if on a quiz or on a test I give you multiple different compounds and I ask you what type of intermolecular forces do these compounds exhibit, right off the bat they all exhibit the London dispersion forces. There's nothing in this world that does not exhibit these type of forces. Every compound experiences this force with other compounds, so keep that in mind. All right. Now the reason why all things exhibit this is because I'm gonna post another video regarding this that explains this really well, a nice animation. But let's assume that we're talking about methane. Methane looks like this. That's methane. Now, if I were to calculate the electronegativity difference for each bond, you would notice that it's not enough to be considered polar. All right, there is no dipole. There is equal distribution of electrons. Remember, polar bonds have an unequal distribution of electrons. These are nonpolar. There's an unequal, or there is an equal distribution. All right, that means that this carbon is sharing equally with this hydrogen, sharing equally with this hydrogen, and the others as well. But there are very, very short moments in time where some of those electrons are going to spend more of their time around hydrogen for a split second. For a split second, some hydrogen or some electrons may revolve more around this hydrogen than this carbon. For a split second, some electrons may revolve around the carbon more often than the other hydrogens. All right, it's just what happens in chemistry. We have these very, very short amount of times, maybe a microsecond. Within a microsecond, this obtains a charge, this obtains a charge, because those electrons are just moving around and they're orbiting around the atoms, and sometimes they spend a little more time on one atom than the other, even though this is a non-polar compound. Those unequal distributions happen within microseconds. Because of that, as a result, this is going to have a partial positive at a microsecond. This is going to have a partial negative at a microsecond. And vice versa for all the other compounds, or all the other atoms. With that being said, if this has a partial positive at a microsecond, it's going to attract another. So let's just say at a very split second, within a microsecond, this hydrogen obtains a partial negative and this hydrogen obtains a partial positive. And remember, they're both nonpolar, but it happens very, very fast. But because of the fact that it still exists, shows that these two would be attracted at a split second in time. All right, this is a van der Waals force. That very, very short attraction between two partial positive charges, one partial positive and one partial negative. It happens very, very fast. London dispersion forces. The reason why all compounds exhibit this is because in nature these happen. All right, hold on really quick.